So one of the things that we need to know for this option, sight and wave phenomena, is all the components of the eye. So here's an eye, and I want you all to fill out the things listed in the diagram as I show them. And I'm going to give a brief description of what each of these does, but then we get a detailed set of notes in the following slides about these functions. So when light comes into the eye, the first thing it hits is the cornea, which is a transparent layer of skin. It provides some assistance in focusing images, and it also is responsible for a little bit of protection. So it's this transparent layer, it's clear, light passes through it. In the anterior, the front chamber here, there's the aqueous humor, and it extends to the iris, which is what we talk about when we say my eyes are blue or my eyes are green. So the iris is what has color, and of course it surrounds the pupil, which is really just a hole in the center of the iris leading to the lens. So the hole leads to the lens, and that hole we call the pupil. Connected to the iris are these, and so first let's say the iris, it's shown as having a bit right here and then another bit down here at the bottom. But we all know that if we were to look at the eye head on, or ion, no, that's chemistry, ions. If you were to look at the eye head on, it would make this circular, the iris would make this circular ring, right? This ring like this. So the ciliary muscle is another ring, and it's actually hidden from view, but it's larger than, it has a larger diameter than the iris. And it's just like the iris. It makes this circle around the lens. So it's a circular muscle, just like a sphincter or any other muscle, any sphincter muscle. And it is really important in the ability to see both near distances and also far distances. So we'll learn about that. It's connected through these ciliary fibers to the lens. So the lens is what focuses the images. And this big chamber here in the back is called the vitreous humor, and it extends all the way to this back surface, which is the retina. And the retina is really, really important. The retina is where all of the magic of the eye occurs. Magic eye. No, that's something else. So the retina is where we actually detect light and respond to incident or impinging rays or beams of light. The retina. Incredibly important. In fact, Darwin speculated that, in his original writings, he speculated that maybe the very first eye consisted only of a retina and some optic nerves carrying signals from the retina to the brain. Now, if you trace a line like this straight to the center of the retina, so the center of the retina, looking at the circle here, here's the center. There's a special spot right here at the center of the retina called the fovea centralis, for center. And we're going to learn about that and what makes it so special. And then over here, there's this interruption, or this break in the otherwise continuous surface. And that's where we have the optic nerves. And the optic nerves connect to the retina, and they go all the way to the brain, and they carry the signals from the retina to the brain, where the brain processes them. But there's this funny thing about the spot right here, where the optic nerves are. Because the optic nerves are designed in such a way that they interrupt this retinal surface, any beams that hit right here are not seen by us. So we call that the blind spot, because when a light hits in this spot, there's no retinal surface to detect those beams. So we can't see whenever light hits that spot. It's our blind spot. So here are the basic functions. The retina is a light-sensitive layer, and it responds to incident or impinging light by sending signals to the brain through the optic nerves. Those signals are then processed, and they're turned into our experience of vision. The lens bends light entering the eye, and it does this so that light hitting the retina, it arrives in focus. So the images hitting the retina arrive in focus thanks to the bending effect, or the refraction performed by the lens. So the lens, that's important, right? The lens is responsible for refracting light to focus it. The cornea is a layer of transparent skin, and it aids the lens in focusing light. And it also is responsible for providing a little bit of protection protective layer. Oops. The lens changes shape to accommodate both distant vision and close vision, and this is a really, really neat process, which we're going to study. The way it works is the ciliary fibers connecting the lens to the ciliary muscle, those fibers can stretch the lens out and change its shape. Now they are controlled by the ciliary muscle, and the way this works is for close vision, that muscle, that circular ring muscle, contracts. Oops. So that circular ring muscle, let me pull the slide up, came out here. The circular ring muscle, it contracts. And when it contracts, it becomes a thicker ring. Okay? So it contracts, it becomes thicker, and it pushes the fibers in, causing the tension in the fibers to be released. And this allows the lens, to become shorter and thicker. So the lens is not stretched out. We'll see this in an example and some drawings. And then for distant vision, those ciliary muscles relax. And when those muscles relax, it becomes a thinner ring. And so it's got a bigger radius because it scrunches out toward the edge. And that causes the ciliary fibers to pull on the lens and make it longer and thinner. So this is hard to understand without a picture. We have contract ciliary muscles on the left, and then I'm going to show you relaxed ciliary muscles on the right. And this whole process I'm introducing here is called accommodation. And accommodation really is the contraction and relaxation of the ciliary muscles to change the shape of the lens in conjunction with the ciliary fibers in order to accommodate both long vision, distant vision, and short vision, near vision. Okay, so imagine that this blue ring here is the ciliary muscle, right? And it's contracted, so it's really big. Just like when you flex your muscles get bigger. So it's contracted, it's flexed, and it's this nice big ring extending out into this region. So here's that ring, here's the ciliary muscle. These red lines are the fibers, and they're connected to the orange colored lens in the center. So I'm looking at this thing head on rather than from the side like we saw before. So I'm going to show the same picture here, and then I'm going to show how it changes when the muscle relaxes. Now when the muscle relaxes, right, it becomes a thinner outside ring. In other words, it's going to become thinner. This inner edge will expand and go farther out. And that means that all of these fibers are going to get pulled outward radially. So here's how that works. And when these fibers get pulled out, they pull on the lens and cause it to flatten out and to stretch out like this. So the lens stretches out, it flattens out almost like a pie crust, right? A flattened pizza pie crust. And over here, on the other hand, what we have is it's not being stretched, and it's more like a lump of dough, okay? So this is like a lump of dough. It's got more curvature. It's not as tall, not as thin. It's kind of thicker and flatter, thicker and rounder and shorter. And over here, it's being stretched out like a pie crust. So again, this produces more curvature, and that helps us with near vision. This has a flatter lens surface, which is good for far vision, distant vision. So accommodation shifts the eye between what we call the near point and the far point. The near point, this is just simply a definition of the limits of our vision. So the near point is the closest a human eye can focus. The far point is the farthest a human eye can focus. And this is how far we focus when the ciliary muscles are completely relaxed, making a very, very thin ring and completely stretching out, flattening that lens. So these are just the limits to our vision. That's all this lingo means. So here's what distant vision looks like. And you see how these rays extend all the way out to infinity, right? Whatever the eye is looking at in this image here, it's so far away compared to the size of the eye that these lines might as well be parallel to each other. Not perpendicular. They might as well be parallel to each other. And that means that they just extend out to infinity. So because of how far away we can see compared to the size of the eye, we just say that the far point is infinity. Now here's closer vision, and of course, the near point, how close we can look, will change from person to person, but we sort of take that value to be 25 centimeters. The pupil is a hole in the center of the iris, like was stated previously. When light enters the eye, it passes through the pupil. The iris is a ring of muscle around the pupil, and in fact, the iris is very similar to the ciliary muscle. It's just another sphincter muscle, another circular muscle, which contracts and expands. The thing is, when the iris contracts and expands, it controls the pupil size, and by doing that, it changes how much light enters the eye. So that's what the iris controls through its relaxation and contraction. When light intensity is low, okay, we can't see very well, the iris causes the pupil to open up to let more light in. Right, so here's how it happens. It relaxes, the iris relaxes, which means it becomes a thinner ring. It's not flexing anymore. And that causes the pupil, the diameter of the hole, to dilate or get bigger. When light intensity is high, we want to prevent lots of light hitting the eye because it gets too intense, too bright. And so what the iris does in that case is it flexes, it contracts, and then it expands toward the center of the eye, and it ends up blocking more of the light because the pupil, the hole, gets smaller. The humors are transparent jellies that nourish the eye, help it keep its shape. The optic nerves, as we saw, they carry signals from the retina to the brain. The brain processes those signals and turns the signals into what we perceive as vision. And they interrupt the optic nerves. They interrupt the surface of the retina, and because there's that interruption, we can't see light that hits that part of the eye, and so we call it the blind spot. Now, the eye plays a really interesting role in the historical argument between creationism and evolution. So feel free to read this. I should say that the force of this argument, the argument of irreducible complexity, the force of the argument relating to the eye is not quite as strong as it once was thought to be, because nowadays we have more of an evolutionary trail leading from simpler eyes to more complex eyes. So this whole argument, it has an interesting role historically, but it's not really so forceful now. Depth of vision is the ability to see things in 3D. We see how far away things are, we perceive depth. And now this is in part thanks to one eye, but it's mostly due just to the use of two eyes. But here's how we have some depth of vision just using a single eye. When we look and we see two objects, right? So if I see two people and one person appears much smaller, I assume they're farther away. So perspective also tells me how far away things are a little bit. For example, if you're on the top of a huge skyscraper and you see this vast, expansive scene out in front of you, then because you see so many different things, you assume they all have to be far away and you're really high up. Relative motion is the same way. If you see something moving faster, it could just be due to the fact that it's closer to your face. However, most depth of vision comes from two eyes, and this is really cool. This is clever. So here's how the depth of vision works. Each eye is separated some small distance from the center of our nose, and so because of that distance separation, each eye views objects in the world from a different angle. So there's this slight difference between left eye images and right eye images. But the farther away the object is, the less that difference is between the two images. Closer objects have more difference between the images. And the brain can use how much difference there is between the left and right eye images to produce 3D vision. And that is so cool. In fact, if you hold your hands straight out, right, hold your arms straight out and put one finger up, left and right, close your left and right eyes successively, one after the other, one at a time. And as you bring your finger in, you see that the finger, as you close your left and right eye, bounces back and forth farther the closer it is to your nose. So give this a shot. And in fact, Magic Eye uses the same principle to produce these 3D images. What Magic Eye consists of is a left eye image of an object, a right eye image of an object, spliced together and covered with this funny pattern to trick our eye into focusing at different areas. So this is how depth of vision works, through the use of two eyes by comparing the left eye image to the right eye image, which are different.